Let's look at simulating this example system we just worked in Octave. And so I wrote a little script here that uses the filter function that we talked about previously in class, and have a vector of the denominator coefficients. And in this case it was just 1 minus 0.8 times z to the minus 1, and in the numerator we had just 1 in the delay form. And here I form my sample vector. In this case I have it go out to 50, and in the first part, if you'll recall, the input was just a vector of 1s. And here run that vector through the filter function using this numerator and denominator, and then have Octave compute the output vector y. So I plot that along with a plot of the theoretical response, and the theoretical response was just 5 everywhere, if you recall, when the input was 1. Now we will notice a little difference when we see the plot, because here Octave is assuming an initial conditions of 0, and recall what we calculated was the everlasting response, excluding the mode terms. So Octave is essentially calculating the switched response. And then for the part B, we had a sinusoidal signal with frequency pi over 6 and a phase angle minus pi 0.2. So I feed that into the filter function. Again, we'll plot alongside that the theoretical output. And then finally we feed in the sampled continuous time signal, and we'll plot that in a third subplot along with our theoretical response. And so let me run this. Hopefully, if we've done everything correctly, these should match. The Octave output is actually shown as a stem plot, and I show the theoretical output, which is also a sequence of values and should properly be shown as a stem plot, but those stem plots would overlap. So I show the theoretical output actually as a line connecting these points. You will notice some differences between the theoretical response to an everlasting input and the solution computed by Octave, because the Octave solution includes the initial conditions of 0. So the state here actually starts at 0 at n equal to minus 1, since this is a first order system. So some minor differences here at the beginning that are to be expected, but good agreement everywhere else, verifying then that our theoretical solution is correct. So again, it's quick and easy to do this type of verification in Octave MATLAB using the filter function, and I recommend it when you're trying to check your homework.